Hello everybody. Today I'm going to talk about another sampling-based path planning algorithm called the RRT star quick, which aims to accelerate the convergence rate of the original RRT star. That's going to be presented by me, Ashraf Faraj, January 20, 2024. So the original problem that we are going to tackle is, as usual, a path planning problem for a kilobot. The start node is here, the lower left, and the goal node is here, which is in the upper right corner. We are going to try to find a collision-free path between these two nodes, trying to avoid the red obstacles. Now, in an earlier video, we discussed the RRT and the RRT star algorithms. We mentioned that the RRT star algorithm does a modification on the RRT, trying to obtain optimal paths. Actually, it can be proven that the RRT star is asymptotically optimal. That is, as the number of nodes tends to infinity, we are guaranteed to find an optimal path between the start and the goal. We also mentioned that this figure right here on the right shows a characteristic shape of the edges of the RRT star tree, in which we can see that most edges are actually now straight lines because they're trying to minimize the total length. So one of the problems of the RRT star is actually the poor convergence rates. So that's why researchers tried to find other methods that attempt to accelerate the convergence rate of the RRT star method. Now, in this video right here, we're going to discuss one such variant. It's called the RRT star quick. We should also mention that the RRT star quick actually has a shape that's actually quite similar to the RRT star tree. Now we're going to discuss the RRT star quick algorithm in detail. First, we initialize the nodes and the edges. We initialize the tree using the nodes and the edges. We also initialize the cost array, and we repeat the following steps for a maximum number of iterations n max. The first step is, as usual, we're going to sample from the free space. Then we're going to find the neighbors within a radius r of the random point xrand. Now here comes the first change to the RRT star algorithm. So the main idea of the RRT star quick algorithm is that we are not just going to search in the neighbors set to find the best parent for xrand, we're also going to expand our search to include the neighbor's ancestors, which is a set given here by the function ancestors. So the function ancestors takes the set x neighbors and returns ancestors of each of these nodes in x neighbor up to a certain degree. So for example, if we say 3, we're going to take the parent of a certain node in x neighbors, then its parent, and then also its parent again. So 3 times. That's what the ancestors actually does. So the main idea is that we're going to expand our search region to find a better parent, and a good candidate for that would be the ancestors of the neighbors. Then we are going to perform a similar rewiring, a similar local rewiring actually to the tree to try to decrease the cost. Now, I call this function modified rewire because, as we're going to see, there's going to be some changes that I'm going to discuss in a few minutes. Then, as usual, if the newest node is actually in the goal region, then save the goal index and keep going until the number of iterations n max and just return the path if the goal is found. Discuss the modified rewire function. So this function takes the tree, the neighbors, and the newly added node x new. First, we're going to initialize a variable called min cost to infinity and min point to -1. Now for each x, for each node in the neighbor set, we're going to define a set called a candidate nodes, which is equal to its ancestors, in addition to the ancestors of the newly added random point. Okay, so this is actually now the set that we're going to search for. We're going to, for each of the candidate nodes in this set, we're going to try to extend from x to x can, if that's possible, and we found that the cost of arriving at the node x from the candidate point x can is actually less than the current cost, minimum cost. We're going to update the minimum cost, and we're going to save the, the candidate point that achieved such minimum cost. After that, we're going to delete the edge between parent of x and x, and then we're going to add another edge that is between the min point and x. We're actually also going to update the cost of x to min cost. And finally, we are going to update all the costs of the children of x because, as we mentioned earlier, there will be a change in these costs once the cost of x has been reduced. So now for the results, the figure on the right shows a path generated by the RRT star quick algorithm on the kilobot example. We can see that the algorithm actually achieved optimal or near optimal performance, just like the RRT star algorithm. Now this should come as no surprise since we are basically the RRT star quick is based on the RRT star and should inherit its asymptotic optimality property. What we're actually interested in is trying to compare the rates of convergence of the RRT star quick and the RRT star. Now we're going to compare the rates of convergence of both the RRT star and the RRT star quick. Now to do this, we cannot actually just compare one run of the path planning problem between the two algorithms because they both use random sampling. So that would be actually irrelevant or might be actually misguiding because we are seeking the mean behavior. So what we did is that we repeated each algorithm for 200 iterations on the same path planning problem. We also fixed the number of iterations after reaching the goal to 1500 to both algorithms. So whenever an algorithm reaches the goal for the first time, it continues modifying and trying to enhance the path for 1500 iterations after reaching the goal. Now the results actually are that first of all, we are going to compare the mean iterations to find the goal between the RRT star and the RRT star quick. We can see that the RRT star quick slightly kind of has a benefit over the RRT star because it finds the goal in less iterations. Of course, the difference is not that significant, so we can't really say that much about the number of iterations to find the goal. However, if we now compare the cost of reaching the goal on the 1500 iterations after reaching the goal for the first time, we can see here that the RRT star quick actually achieves a lower cost with the same number of iterations as compared to the RRT star. So this means that the quick RRT star actually approaches the optimal solution faster than the RRT star algorithm. And this would indeed confirm that the quick RRT star actually improves the rate of convergence of the normal RRT star. Now for the conclusion, in this project, we discussed the RRT star algorithm in detail. We also implemented and tested this algorithm on the kilobot path planning problem. Finally, we compared the RRT star quick and the original RRT star in terms of convergence rate. We found that the RRT star quick was actually faster than the RRT star in reaching the optimum solution. It should be noted that the RRT star quick actually achieves this enhancement or acceleration in the convergence rate at the expense of increasing the computation, since we are now checking more nodes than we did in the original RRT star. And that's it for this project. Thank you for listening.